Hello everyone, I'm Jamie Talbot from Arup, based in the UK and the project manager for the Oasys LS-DYNA environment, and welcome to our update webinars. This is a series of webinars to provide you with the latest updates for LS-DYNA and the recent version 17 release of the Oasys suite. This software is now available to download from our website. We would normally share this information at the users meetings we hold in various regions, but with the current COVID-19 situation, this is unfortunately not possible. On that note, I hope you, your family, friends and colleagues are all keeping well and staying safe. We are hoping to reschedule some users meetings to later in the year, so please keep an eye on our website or subscribe to our newsletter for any announcements in that respect. I have some general updates and information to share before starting with the main webinar programme. The first, which may be obvious from the new logo on the slide, is the Ansys acquisition of LSTC in November last year. This may have come as a surprise to many people, but the overall message from Ansys and Arup is one of business as usual and customer focus. Our LS-DYNA customers will continue to have the full access to our LS-DYNA expertise, support, training, webinars and other resources, and we look forward to continuing this support in the future. Ansys and LSTC are a good match. Even before the acquisition, the development goals of Ansys and LSTC were very well aligned. John Hallquist's objectives for LS-DYNA were that of one code, using LS-DYNA multiphysics solvers for all applications. This fits really nicely with Ansys's goal of a unified simulation platform for complex multiphysics solutions. Arup and Ansys are working together, and our Ansys colleagues will be invited to the users meetings rescheduled later this year. You can of course meet the Ansys team at the now virtual International LS-DYNA conference on the 10th of June. Please see our website for further details. The second update is our response to the COVID-19 situation and how we can help you while many of us are adapting to new working arrangements. All of our face-to-face training has been cancelled for the time being, but our webinar programme continues as normal. The next normal webinar is the Advanced Implicit LS-DYNA on the 7th of May. Please register from the training section of our website highlighted here. Also on our website, you'll see a new link on the top navigation to our COVID-19 page. On this page, there are many hints and tips that may help you with your LS-DYNA analyses and use of the Oasys software while working away from your normal networks and compute resources. We're also pleased to offer a working from home license for the Oasys software. If your organisation has bought an Oasys license, you can follow this link and complete this form to have a license emailed to you directly. The Arup support team, although mostly working from home, are still fully operational. If you have any problems with working from home licenses or you have any other Oasys or LS-DYNA support queries, please do not hesitate to contact us. Here's our direct support contact details. These and the contact information for our distributors are also available on our website. This is a good opportunity to welcome Rekha Mukhari to our support team. Rekha is based in Hyderabad and is likely to be the first point of contact for India support queries. Rekha also spends about 50% of her time helping the UK team out, so I expect Rekha's name will already be familiar to some of you watching these webinars in India and the UK. Welcome Rekha, and thanks for your hard work so far. Moving on to the main webinar programme, Richard Sturt will be presenting the LS-DYNA update straight after this intro, but you may notice a difference with the Oasys theme talks. As the Oasys suite continues to become more integrated, many of the new features and enhancements benefit the whole LS-DYNA workflow rather than the individual products. For this reason, we've moved away from the pre and post theme demonstrations to how the new features and enhancements aid the full workflow. Before handing over to Richard, I would like to thank Isheng Yi from LST. Isheng was all set to present this material in person at the UK event we had planned for March. So thank you Isheng for sharing this material, and thank you Richard for offering to present on his behalf. I'd also like to thank our developers and project managers, Gavin Newlands and Alistair Parks, for their hard work creating and presenting the Oasys material. Finally, a huge thanks to Hazel and Marta for their tireless efforts bringing this webinar programme together at a very difficult time. To all our customers, distributors and partners, please stay in touch, stay safe, and I hope you enjoy the webinars. Here's Richard Sturt to present the LS-DYNA update.
Well, hello, this is Richard Sturt from Arup, sitting here at home recording this webinar about LS-DYNA. It's a shame we can't have our usual gathering, and I'm very sad about missing the dinner, but hopefully we'll be able to make up for it later in the year, once it becomes safe to hold large gatherings again. In the meantime, you'll have to make do with this webinar. Now, for the LS-DYNA talk, the original plan was for Isheng Ye from Livermore Software Technology to come over to the UK and present at the users meeting. But obviously we can't do that now, so instead I'm going to be presenting his slides. Before getting into LS-DYNA itself, I'll show the release schedule and talk a little about LS-Opt and LSTC's downloadable models of dummies, barriers and so on. Here are the recent releases of LS-DYNA. New developments go into the next major release, such as R9, R10 or R11, and each major release then gets one or two minor releases to fix bugs. Many customers are transitioning from 7.1.3 to 9.3.1 as new projects start, and R11.1 is popular among customers who need the latest features. Later this year, we are expecting the first release of R12. LS-Opt is the product that sits around LS-DYNA and manages optimization, variability or robustness studies and parameter identification. I'll mention two features that have been added within the last couple of years. The first comes from the world of machine learning and has the rather off-putting name of Support Vector Machine. It sounds to me like the name was invented by a 6-year-old Star Wars fan. Anyway, Support Vector Machine is a method of classification, which means rules for predicting which of two binary outcomes will result from a given combination of inputs. Typically, will this given set of inputs give me a pass or a fail? This is different from meta-modeling, which seeks to predict the value of a continuous variable from a set of inputs. As a simple example, the acceleration output might be approximated as a linear or quadratic function of the thicknesses of certain parts of the model. In general, compared with meta-modeling, classification can adopt more intricate functions to separate the passes from the fails, but it gives little or no information about the value of the output variables. A simple binary choice can be more appropriate when we only care about whether a given event happens or not. In the case of an aortic aneurysm, that event would be rupture. Or when human judgment is involved, such as, do we call this mode buckling or crushing? Support Vector Machine, or SVM, includes a bunch of mathematical tricks for finding complex shaped boundaries between the passes and the fails, and for quantifying whether the proposed boundary does a good job or not. This makes it well suited to problems where the relation between inputs and outputs is highly nonlinear. In this case, the two input variables shown as the x and y axes of the graphs are the thicknesses of the side intrusion beam and the floor, and the output is deemed to be a pass if the intrusion at the two measurement points comes out below the target values. 400 runs were used as a training set, from which the SVM method produced the boundary line shown in blue in the lower right graph. The same set of 400 results was fed into a neural net, which came up with a different classification boundary shown in the lower left graph. Then 20,000 runs were performed, giving the result in the bottom center graph. Comparing the red-green boundary against the ones on the left and the right, the SVM method on the right has done a better job. Classification into pass and fail can help speed up multidisciplinary optimization. You can set it up to analyze the load cases that are quick to run first, which in this case is NVH. Then any designs that fail at the first hurdle don't go forward to the more time-consuming crash analysis. And because of the more complex classification boundary achieved by SVM, you can obtain a better optimization result. The second feature I want to mention relates to LSOpt's parameter identification capability. That's when you ask LSOpt to determine the input parameters which give the best match to a given test result. The so-called dynamic time warping sounds like we're back on a Star Wars theme here. What it really means is that when the program decides how good a match there is between the graph from analysis and the graph from test, it can take a more flexible approach if the peaks are a little misaligned on the time axis. It's not looking for a match between result at time t against analysis at the same exact time t. Here's an example where we have results from tests on 3 different stress paths, which are uniaxial tension with the dog bone sample, shear with the sample containing 45-degree slits, and biaxial tension from a sphere pushing into a disk. We want to find the material input parameters for the gizmo functions in MAT-AD-erosion that best match the softening and failure behavior across all 3 cases. These near vertical drops in the curves make it quite challenging for the more traditional algorithms to know whether they've got a good match. Using dynamic time warping, a good match was obtained after 15 iterations. Moving on now to the finite element models provided by LST, most of the presentation material on the barrier and dummy models was shown last year, so this is going to be just a very brief overview. These are the barrier models. Many of them are available as shell element models for greater accuracy. Ongoing work on the dummy models include the hybrid 3s, which are being updated and re-released regularly, and there are models of WorldSid 3-year-old and hybrid 2 under development. There's now a family of tyre models available. They can be used for crash analysis, driving simulations, or other purposes. The models are fairly detailed, including the structural layers and solid element rubber tread, and come in at around 200,000 elements per tyre. These are the sizes that are available so far. If you're interested in this, go to the page on LST's website shown in the hyperlink at the top of this slide. Moving on now to LS-DYNA itself. I'll cover a number of topics, focusing mainly on what's new in the most recent versions of LS-DYNA. The topics presented are only a small subset of the actual ongoing developments, and Isheng and I have tried to pick out the things that might be of most interest to you. Implicit analysis is still a big focus of development. This includes making big models run faster on large numbers of CPUs. I won't talk through the detail on this slide, but the graph shows wall clock time for this 35 million element model as a function of the number of processors, going up to a couple of thousand. The difference between the purple curve and the green curve shows the progress made in the last 2 years. The number of keywords available in implicit analysis continues to increase. Among the recent additions is MAT-ARP adhesive. The increased use of implicit analysis is driving efforts to provide ever more sophisticated elements, including these cubic solids. Composites continue to provide many challenges for accurate modelling, especially when the failure modes involve delamination. This slide is describing a modelling technique that has shown good results. Each ply is modelled with thick shell elements. They're the ones that look like bricks but behave like shells. And the plies are glued together with extremely thin cohesive elements. This new feature models a type of sensor used in car bumpers to detect pedestrian impact. The pressure in a sealed tube will increase when its volume gets reduced by an impacting object, And this new feature also models the pressure wave effects that occur in the tube when the load is applied suddenly. For implicit analysis, we recommend using the contact types that include the word mortar. These now support element erosion, so that if a solid element gets deleted, the contact passes to the next element underneath. And it's the same with the edges around a shell element mesh. Now moving on to tie-break contact, which is sometimes used to model welded or bonded joints that can break apart. There's a new option suitable for adhesive bonding where you don't have to model the adhesive as elements. The bond characteristics are modelled within the tie-break contact. There are a number of additional features in the soft equals 2 contact, including the ability to have different friction values on each side of a sheet material. MATLAB erosion was first introduced to enable users to tell LS-DYNA to delete elements when they reached a simple failure criterion or if they were misbehaving in some way. It has historically been limited to solids and shells and only the simpler element formulations. Now it's been extended to cover a much wider range of element formulations and types, including beams. It's now available also with constrained tied nodes failure, which enables solids to break apart from each other when the failure criterion is reached, like in the animation here. Over the years, MATLAB erosion has grown some sophisticated damage models, especially Gizmo, which is very widely used, and this has now been split off into its own keyword for clarity, MATLAB damage Gizmo. The old keyword will still work, this one's just clearer. It has some new features too, including the one in the picture at the bottom of the slide, whereby you can define a stochastic variability of damage properties in each element. This is a feature that's still under development, not quite ready to use yet. When elements reach a failure criterion, they would normally get deleted, but that can give very unrealistic results for some types of problem. In reality, the broken bits of material still have mass and can still pile up and generate friction against each other. And if we model the elements disappearing, you miss an important contribution to the load. With this new feature, instead of being deleted, the failed elements detach themselves from the surrounding mesh and become rigid. There are other approaches already available, such as SPH, which would be able to model this kind of response, but it might still be useful to have this new technique available where there is a strong reason to stick with normal finite elements. This is a new material model focused on damage and failure of metals. It can be calibrated against experiments where the failure properties seem different under pure tension versus bending conditions. Developments related to human body models and medical applications are very much ongoing. This material model is for blood vessel walls and other biological materials that are reinforced with directional fibers. Modelling of laminated glass windscreens is of great interest for pedestrian safety. This material model is for the glass itself. You'd use a different model for the stretchy polymer interlayer. The main nonlinearity here is cracking due to tensile stresses. The latest development is that the tensile strength of the glass increases at high strain rates, which gives a better match to tests. Seatbelts are generally modelled with 4-node seatbelt elements. The material card, mat seatbelt, has inputs that link to the same fabric model as used for airbags, mat fabric. When applied to seatbelts, the fabric model can sometimes wrinkle up in a non-physical looking way, but there are some new options that straighten it out. On the mat seatbelt card, you can request form 12, 14, or -14, which have the same meanings as the input parameter with the same name in mat fabric. They all give a better response than the default. Form -14 has the additional capabilities of modelling an elastic coating, like the liner of an airbag, which can further increase the stability. These three models compare the different settings of form. On the right is the old setting. Look at the lap belt and the section between the shoulder and the D-loop. On the left is the newest setting, which shows a great improvement. Setting up tension in bolts has historically been something of a challenge. The old-fashioned method is to apply a thermal expansion coefficient and cool the bolts to make them shrink, but you had to iterate a bit to find what temperature drop would produce a given tension in the bolt, and this depends on the stiffness of the surrounding structure. Then, initial stress section came along. This can reliably provide a given axial stress, but until recently the bolt had no shear stiffness or strength during the initialization process. This was fixed in R10 by the input parameter IZ shear. In R11, the option to allow the bolt to generate moments was added, and the keyword now works in implicit analysis as well as explicit. If you've ever used rigid bodies to restrain a model, you'll know that SPC restraints can be applied on the MATRigid card. But until recently, there wasn't a good way to output the reaction force caused by the restraint. Now there is. LS-DYNA can output the forces to the binout file as if you'd defined a velocity boundary condition with zero velocity. Now I'm going to move on to scalability of MPP solutions. The efficiency of running problems on multiple processors is a very important topic for most of us LS-DYNA users. You probably know that MPP parallel works by cutting the model into so-called domains, which are shown by the different colors in the car model here, and setting each computing core to work on one domain. LS-DYNA is pretty good at cutting up the model so that each domain takes about the same effort to calculate, since the solution effectively has to wait for the slowest processor. That's called load balancing. Now, we might hope that 1,000 processors would run a model 1,000 times quicker than one processor, but it never turns out like that. A big factor is communication between processors, especially over the network. Communication is needed for what's happening at the boundaries between the domains, and also for contact. For example, an element in the red domain might contact an element in the blue domain later in the calculation, so the red processor and the blue processor have to talk to each other about that. This becomes a bigger drag on performance the more domains you cut the model into. Hence the MPP/SMP hybrid version of LS-DYNA. We cut the model into fewer domains, so each domain is larger, but we give each domain to multiple cores within a single compute node, and have those cores work together as a team using SMP parallel. Why SMP parallel? Because all those cores can see the same data, so there's no additional communication effort within the team. This will result in better scalability on large numbers of processors. For some types of models, scalability becomes markedly worse during the analysis. In this example, the graph shows the wall clock time between consecutive D3 plot file outputs. By the end of the analysis, it's crawling along 6 times slower than it was at the start of the analysis. This can be caused by the load becoming unbalanced. For example, one processor may become a bottleneck if it's trying to deal with an unfair share of contact compared to all the others. Or it can happen because the communication needed between the domains increases dramatically. In both cases, the division of elements into domains that was optimum at the start of the analysis becomes far from optimum later on. But help is at hand. You can now tell LS-DYNA to stop the analysis, make a new decomposition optimized to the current condition of the model, and continue from where it left off. This is called re-decomposition. Now, to do this, LS-DYNA has to write out a massive file to restart from, wash out all its memory tanks, and read the file back in, so there is an overhead there, and you wouldn't want to do this too often during a simulation. However, if you are running the type of analysis that becomes very much less efficient as it progresses, this may be worth considering. Here is the outcome for the model on the previous slide. When re-decomposition is used, there is a factor of 2 reduction in the total wall clock time. In this case, the re-decomposition happens 20 times during the analysis. These are the related keywords: star control MPP decomposition re-decomposition. I thought this would be the keyword with the greatest number of letters in the whole of LS-DYNA, but amazingly it's not. There's another one that's 10 letters longer. This feature uses the same restart file as the so-called full deck restart. So there is some flexibility about not just doing the re-decomposition, but at the same time modifying the model in some way, or rerunning certain parts of the analysis at a later date. There is a further development underway at LST, in which the analysis dynamically shuffles elements from one domain to another during the solution, without needing to stop, write and read large files. This dynamic re-decomposition is not yet ready to use, but watch this space. I'm going to summarize the frequency domain capabilities very briefly and show a couple of examples. The basic modal analysis can be used to feed a number of solution types that work by modal superposition, including frequency response function and steady-state dynamics. The steady-state dynamics now has an option to use direct solution instead of modal superposition. There is a random vibration capability, and there is response spectrum analysis, in which the peak response is found by summing modal contributions based on an input spectrum curve. That's a method used in earthquake engineering, among other applications. There are various acoustics capabilities using boundary element or finite element methods. Stress results can be combined with load time histories or spectra to calculate fatigue utilization. Here's an interesting example. LS-DYNA's electromagnetic capability drives a speaker, while the radiated sound is predicted by the boundary element acoustic solver. This is something I didn't know LS-DYNA could do. Vibration is produced by a structural model of a xylophone, which drives vibration in the air analyzed by the acoustic boundary element solver. And the sound pressure time history can then be converted into a sound file by LS prepost. Here we go. The next topic is modelling the batteries of electric vehicles. One of the safety issues that needs to be analysed is the possibility of short circuits causing runaway heating leading to fires. That can potentially be triggered by deformation of the battery, for instance, during a crash. One approach is simply to put a big protective structure around the battery and design for no deformation whatsoever. And for that, you need only the regular mechanical analysis techniques, but the structure might be over-designed. If instead you model the multi-physics effects that can lead to fires, it may be possible to relax the criteria somewhat. For this type of analysis, you need LS-DYNA's electrical and thermal analysis coupled with mechanical. The models can then be used to look at abuse cases, and by adding fluid flow into the analysis, you can look at cooling as well. This whole topic of battery modelling is one of the strongly growing areas of LS-DYNA application, and many specialist capabilities have been developed to support it. There's a big challenge around scale. where the layers that need to be modelled within a cell can be as little as 20 microns thick, while the whole battery may be of the order of a metre across. Modelling a whole battery, including all the layers within the cells, just isn't possible with today's computers, so a multi-scale approach is needed. For instance, the detailed layers in the cells are important electrically and thermally, but less so structurally. So the model can use a layered thick shell for the mechanical analysis, while automatically creating multiple layers of solid elements for use in the electrical and thermal calculation. The battery macro model, so-called BAT-MAC, enables all the layers of a cell to be modelled by just one or two elements. The BAT-MAC can still model the mechanical, electrical and thermal effects, but you'd need to calibrate its properties against a detailed cell model first. Then the BAT-MAC elements can be used in a model of a whole module or pack of cells. For cooling analysis, the heat generation effect of the battery cells can be modelled without meshing the cells at all, using this keyword *EM Randall meshless. Now I'll say a few words about LS-DYNA's CFD capability. Now you might ask why CFD capability was added to LS-DYNA in the first place, when there's already several good CFD codes out there. One reason is that it's part of the drive towards multi-physics. So for instance, there are many fluid structure applications where normal CFD codes couldn't model the deformation of the structure. But the objective is also for LS-DYNA to be cheaper and faster for purely CFD applications as well. So that includes the typical external flow applications shown in the upper set of images and the free surface applications in the lower set. The CFD keywords and finite elements can be combined in the same model for fluid structure interaction problems. In the top left example, packages are dropped out of a moving plane and they fall differently according to their weight relative to the aerodynamic forces. The pictures with the white packages are from experiment and the yellow ones are from analysis. In the middle is a parachute and in the lower left is a heart valve. In all of these cases, the structure moves or deforms in response to the forces from the fluid. The different shape of the structure alters the fluid flow, which in turn changes the forces on the structure. Fluids analysis can also be combined with thermal, as in the examples on the right. In the upper right example, water is flowing through a pipe, carrying heat away from the tool in a forming process. There are some experiments by the American Food and Drug Administration for calibrating computer models of products that will come into contact with blood. Here we see results from LS-DYNA's CFD capability compared to the experiments for flow through a nozzle. This is a model of a centrifugal blood pump. Some comparisons with experimental results are shown in the graphs at the bottom of the slide. The challenge here for a CFD model is the moving impeller. In typical CFD models, only the fluid moves, while the structure is normally just like a fixed boundary condition. This is modelled using a new feature called sliding mesh. It enables the yellow part of the fluid mesh to rotate with the impeller, while the blue mesh remains stationary. This minimizes the need for remeshing during the analysis. Fluid can flow freely across the interface as if the fluid mesh were continuous, a bit like stresses flowing across a tied contact in a structural model. Other new features include periodic boundary conditions and a wave generator for free surface models, which should be useful for offshore structural applications. My final topic is about a newly developed capability to link to other software. First, I need to introduce the coupling mechanism, which is called Functional Mockup Interface, or FMI. It is a standard which defines a format for data exchange between programs. and it also defines the transmission mechanism, the pipe through which the data can be sent. Having the interface enables a program to transmit and receive data that other programs can understand, provided that they also have the interface. It therefore eliminates the need for specific coding to enable software A to talk to software B. The name Functional Mockup Interface implies that it would mainly be used for sharing design data among different teams along a supply chain, and that is indeed one of its uses. But what I'm going to talk about today is using FMI for exchanging information while the two programs are running an analysis, so-called co-simulation. Here are a couple of examples. You will see the term FMU on these slides. This stands for Functional Mockup Unit, which is a set of communication instructions specific to a particular model, which is formatted in accordance with the FMI standard. In the upper example, LS-DYNA is interacting with a specialist hydraulics code to model a pneumatic drill. The hydraulic model sends pressure to LS-DYNA, which does the dynamic finite element calculation and sends displacements and velocities back to the hydraulics code. In the lower example, the Simulink add-on to MATLAB is used to model a control system and drive a robot arm. It passes forces to LS-DYNA, which calculates the motion of the arm and sends feedback from sensors to MATLAB. It works like this. Your LS-DYNA model includes certain keywords that start with *co-simulation. You initialize the model in LS-DYNA, telling it to output a functional mockup unit, or FMU, and then stop. The FMU is specific to the model and to the settings on the co-simulation cards, which will include things like LS-DYNA will receive the force to be applied on node X, it will run for 1 millisecond and then send back the displacement and velocity of nodes Y and Z. The FMU also sets up the pipe through which the two programs will communicate. When you set up the control logic wiring diagram in Simulink, one of the types of block you can create is called FMU. You select the FMU file written by LS-DYNA, and that tells Simulink all it needs to know about what the inputs and outputs are and how to communicate with LS-DYNA. You then launch LS-DYNA again, this time with settings on the co-simulation cards that tell it to go ahead with the analysis and where to find the FMU. You also launch MATLAB. Because both programs are now working with the same FMU, they talk to each other and exchange data as required. The next few slides come from a collaboration between General Motors and ANSYS/LST. The last application I'm going to show is LS-DYNA connected to this driving simulator called ANSYS VRX. The simulator has a human driver with a virtual test vehicle. The driving conditions are taken from real-world recordings. VRX can be used for testing active safety systems such as collision avoidance or automatic braking based on radar, LiDAR, etc. Various vehicle types with their different dynamic characteristics can be modelled. In this example, an LS-DYNA vehicle model containing an occupant is coupled with VRX via the functional mockup interface. In the pre-crash phase, VRX determines the vehicle dynamics and LS-DYNA works like a slave, so essentially VRX is prescribing the motion of the vehicle. If the vehicle suddenly applies the brakes during the crash avoidance phase, the occupant will be thrown forward to some extent. When the impact occurs, LS-DYNA takes over control and simulates the crash. So this co-simulation enables the effect of pre-crash dynamics on the occupant position to be included in the crash simulation. This type of co-simulation could be used to explore different accident scenarios and different crash mitigation strategies. VRX could send the signals to belt pretensioners in the LS-DYNA model, for example. This could be more important in autonomous cars, where the range of possible occupant positions is much greater. If you had an LS-DYNA human model sitting in the seat, you could also imagine being able to make the model react to the upcoming crash by tensing muscles, or possibly by screaming and hiding behind the seat. Well, that's the end of this webinar on new features of LS-DYNA. Thank you very much for listening.
Thanks for that, Richard. Some exciting updates as usual, and I look forward to seeing the Starscream keyword implemented in LS-DYNA soon. Thanks also to Isheng for providing the ANSYS LST updates for us to present on his behalf. If anyone has any questions on the material presented or related LS-DYNA queries, you can contact us at any time through your normal support channels. I hope you all enjoyed that webinar update. Please don't forget to join us at the other Oasys webinars over the next 2 weeks. Thanks for watching. Goodbye.